Have you ever tried pushing a stalled car or pulling open a jammed drawer? That invisible effort you apply to change something's motion, that's what physics calls force. Good day, learners. Today we begin an exciting exploration of force, one of the most fundamental concepts in physics. Force isn't just about strength, it's about the cause of motion, the reason why things accelerate, stop, bend, or change direction. Force, in physics, is defined as any interaction that, when unopposed, changes the motion of an object. It's a vector quantity, meaning it has both magnitude and direction. The C unit of force is the Newton. And here's how it's defined. 1 Newton is the force required to accelerate a body of 1 kilogram mass by 1 meter per second squared. Remember, force can be classified into different types: contact forces like friction and tension, and non-contact forces such as gravitational, electric, and magnetic forces. Whether you're kicking a football, magnetizing a nail, or dropping a book, you're witnessing the effects of force in action. Let's clarify the different types of forces you'll meet in physics. First, contact forces. These act only when two bodies touch. Friction resists motion at the surfaces in contact. Tension pulls along a rope, string, or cable. And the normal reaction pushes perpendicular to a surface, supporting an object against gravity. Now, non-contact forces. These act across a distance without any physical contact. Gravitational force pulls masses toward one another. Electrostatic force attracts or repels due to electric charge. Magnetic force acts between magnets or moving charges within a magnetic field. We also distinguish between muscular and mechanical forces. Muscular force is produced by living beings, your biceps lifting a box. Mechanical force is delivered by machines, a jack, a motor, or a hydraulic press, often providing greater and more consistent output. Finally, balanced versus unbalanced forces. When forces on a body are balanced, the net force is zero, so there is no change in motion, the object stays at rest or continues at constant velocity. When forces are unbalanced, the net force is non-zero, and the object's motion changes, it speeds up, slows down, or changes direction. Together, these categories help us analyze who or what is pushing, pulling, and how motion responds.
What does force actually do? First, it changes velocity, either speed, direction, or both. Any such change is called acceleration. Second, it can deform objects, squeeze or stretch a spring, and you are witnessing force reshaping matter. Third, it can produce equilibrium. When all forces cancel each other, the body remains at rest or continues uniformly straight. Industry harnesses precise forces every day. Hydraulic presses form metal sheets. Cranes lift heavy loads safely. For a vivid example, consider a car crash. Unbalanced forces act for a brief time and change velocity drastically, which is why safety features are designed to manage those forces over a slightly longer time, reducing harm. Newton's first law states, a body remains at rest or in uniform motion in a straight line unless acted upon by an external force. The built-in stubbornness to change motion is called inertia. Here is the key idea. To change velocity or direction, a force is required to overcome inertia. Try the classic coin and card demonstration. The coin rests on a card placed over a glass. Flick the card swiftly. The card moves away, but the coin, due to inertia, drops straight into the glass. That moment perfectly shows that force is the cause that overcomes inertia and induces motion. Now we connect force and acceleration precisely. Newton's second law says the rate of change of momentum of a body is directly proportional to the applied force and occurs in the direction of that force. In simpler words, force equals mass into acceleration. This immediately tells us two things. Larger forces produce greater accelerations on the same object, and heavier objects require more force to achieve the same acceleration. The unit once again is the Newton, defined as 1 kilogram meter per second squared. Compare a cricket ball and a football. If you apply the same push, the lighter cricket ball accelerates more because its mass is smaller. Quick reflection. If the acceleration doubles while mass stays the same, what must have changed? The applied force doubled. Every interaction involves a pair of forces. Newton's third law states, for every action there is an equal and opposite reaction. These forces are equal in magnitude, opposite in direction, and they act on different bodies. When you walk, your foot pushes the ground backward, and the ground pushes you forward with an equal force. This reaction propels you. When a gun fires, the bullet is driven forward while the gun recoils backward. A common misconception to avoid: action and reaction do not cancel each other because they are not acting on the same object. They are a pair connecting two interacting bodies. To solve real problems, we first learn to see forces clearly. A free body diagram is a simple sketch that isolates a single object and shows all forces acting on it as arrows. Each arrow is a force vector with a direction and a length proportional to its magnitude. On the sample diagram, identify the weight acting vertically downward, the normal reaction acting perpendicular to the surface, and any tension or friction as appropriate. Why do we draw these? Because once every force is laid out cleanly, we can determine the net force and predict the motion. Engineers and physicists rely on this method in everything from bridge design to robot motion planning. Let us tie it all together. Force is a vector cause of motion or shape change. Forces come as contact and non-contact types, and whether they are balanced or unbalanced decides if motion changes. Newton's first law explains inertia and the need for an external force to change motion. Newton's second law links force to mass and acceleration, making predictions quantitative. Newton's third law reminds us that interactions come in equal and opposite pairs acting on different bodies. Free body diagrams turn messy real situations into clear, solvable models. From walking across the room to launching rockets into space, force is the invisible push and pull shaping every motion we observe. Before we move on, pause and ask yourself, if I can name the forces, sketch them, and decide whether they balance, can I predict what happens next? If the answer is yes, you have the essence of dynamics in your hands.